may have already read the meetup portion description, but Dr. Zhenwan Zhu graduated with his BS degree in physics from Nanjing University and a PhD in optics and photonics from the College of Optics and Photonics at the University of Central Florida. His research includes the development of novel optical imaging systems and the companion numerical methods for the extraction of information of interest from the measurements. During this time, he developed an interest in amateur astronomy. After graduation, he continued as a research scientist at UCF, working on the development of an integrated photonic circuits and electronic peripherals for analog matrix computations, targeting high-performance computing and AI applications. He's currently working in the semiconductor industry on micro-optics design, fabrication, and metrology. So I'll turn the floor over to Dr. Zhu.
Thank you so much for the introduction, Larry. Yeah. All right, thank you all for coming. And yes, so I was a physics major when I did my undergraduate study. And when I was trying to decide what field of study I should get involved in for my graduate study, I was quite a bit of, a lot of choices, but eventually I settled on optics. One of the major reasons was I did very horrible at quantum mechanics when I was an undergraduate student. And lots of things in solid-state physics, they require quantum mechanics and those things, and I wasn't so good at it. However, there was one class I excelled at it. Guess which one? Electromagnetism, about Maxwell equation. So that made the decision to pursue an optics as a further study for my graduate program. So there was only 3 dedicated graduate schools with a degree in optics and photonics: the University of Rochester, University of Arizona, and the University of Central Florida. Among them, University of Central Florida's optics program was the most recent one. It was newly established only back in the 1970s. And the other 2 are much older. And, but they offer an easier admission, so I got into it, and that's how I end up with my profession in optics and photonics. So today I will introduce some history and fundamentals in optical imaging, which actually was closely related to what I did for my graduate study, my PhD thesis. Specifically, I'm going to introduce some quantitative metrics to describe the quality of an imaging system and its sensitivity to optical alignment. And you can see that these things are all intertwined together with, throughout the presentation. And leveraging my training in imaging system, I will share some motivations and design considerations that went into building my amateur astronomy setups. And from the early prototypes to the latest one that Astronomical Imaging and the Metrology System aims, and along with the lessons I learned in each of the iterations. So let's get started. So the field of optics actually dates back centuries ago. And just like many branches of science, optics remained as an empirical study for centuries old until the Renaissance and the scientific revolution that followed afterwards. And before Renaissance, actually during the ancient Greek time, Euclid actually proposed 7 axioms of optics, and if you read them, they kind of look like more like an empirical description of that. Of course, some of them do make sense, and we're still using these concepts. For example, number 1, the lines can be drawn, or the rays can be drawn in a straight line to the object. That is actually a fundamental principle in geometric optics. Basically, the light travels as a rays along a straight path in a homogeneous medium. Number 2, for example, those lines falling upon an object form a cone. And number 3, those things upon which the lines fall are seen. Actually, these 2 represents the light cone emitted from an object point and the light cones converging onto an imaging point. And those actually are important concepts in geometric optics that explains how images are formed. And then the rest of them, they are kind of, well, we now have more rigorous mathematical description for them. And here, down here, you can see that a medieval European drawing of an optical diagram, they start to realize that with a glass sphere or a sphere full of water, you can already form an image of a point here, down here. So if you look through a crystal ball, like glass ball or crystal ball, you can see the items being magnified, or you can see the rays from the sunlight as focused to a point afterwards. In the medieval time, the Europeans start to realize these things. And what's common about this, even though they didn't get the rigorous mathematical description for the optics field, the common theme they have already recognized is that optics are the components that will deceive your eyes. In other words, optics always form an image of the object. It's never the real object. So through an optics, you never see an object. You are just seeing an image of the object. No matter it's a pinhole camera or it's a single lens imaging formation that people studied a long time ago. So this theme remains the same. Optics deceives your eyes. Okay, if something is empirical and deceptive, how can it become a formal field of science? And especially when the image formation is explained in such empirical ways, how it can become a real science. So for the optics part, I'm going to deal with that later. But first, I will introduce something, and that is something we now look at it through the modern optics way. What is an imaging system? Starting in the early 1900s, modern optics provides a new perspective towards image formation. We have the centuries old people saying, hey, you have a light emitted from the cone of an object, and then the light converges onto a point on the image plane, right? Those things. Now this process has been quantified. The process of imaging is as follows. An object, shown here, can be dissected into numerous points. Each individual point, after going through your optical system, no matter what are the components in this optical system, each point of the object, after going through an optical system, will give you a speckle. Will give you a speckle on the image plane. And this speckle, we now call it a point spur function. This is named following the tradition in electrical engineering, in which they have the name impulse response, describing how, if you send in a pulse, what will be the outcome electrical signal from this pulse. It's an analogy to that. So each point in the object will produce a speckle on the image. And now the image formation is a superposition of all these speckle patterns from the object. Okay, so that was actually the very basic concept I learned when I joined the graduate program. And that's not enough to do a thesis on that, right? Because they are still descriptions. They are not mathematics. Now we come to a bit of mathematics, and then that becomes a thesis topic. So imagine we have an object, and then this object has 5 points. Now, I have some mysterious optical system in which each point here will be mapped to a speckle pattern or the point spur function looking like this on the image plane. Now, the superposition principle basically will say, hey, this point have a speckle like this point has a speckle like this point in the center has a speckle like this, but in the center. So now you add up all these things, you form the image. And this image, if you have a point spur function like this, it is indeed a blurred version of your object. Now, this linear superposition can be represented as a matrix equation. So now let's brush up some of the linear algebra backgrounds. So imagine that this object, this is 2D object, right? We can always vectorize it into a vector. Let's say, remember the old time the TVs, it scans out a 2D image line by line. We can vectorize this object. So we scan it out line by line. In the field of imaging, the convention is actually the Fortran order. Yes, because Fortran was the first language to use for scientific computing. Well, at least I know of. So in the imaging community, people will dissect the object, a 2D image, through the column order. So you dissect it like this, and then this next column, and then the next column, and next column, following the Fortran order. So now you get a vector. You can similarly dissect your speckle pattern or your point spread function also along the column major order, and then each point on the image plane is represented by one column in this imaging matrix. So let's say this pixel will form a blurred pattern somewhere here on the image plane, and that blurred pattern is actually your point spread function being dissected or vectorized along this column that corresponds to the corresponding location on the image plane. So that's a bit of math in there, but this math actually gives a quantitative analysis, a quantitative description of image formation. So when I learned this, okay, I thought to myself, great, why do I still need to learn optics? Right? If I already know how the image forms from the object through this matrix here, and if I have horrible optics, let's say, the optics produces such a blurry image, right? So it means every point in the object is mapped to such a large speckle on the image plane. The resulting will be a very blurry image. If I have that, but I have a description of this in a mathematical equation here, why do I need good optics? So that's actually an interesting problem that actually puzzled me for almost 2 years. Starting the time I entered my PhD program until I passed my candidacy exam. That's the question that puzzled me. Why do I still need a good optical system? So let's first take a look at an example in which we don't need a good optics system, and this method actually works. So back in 2022, our lab actually was tasked with constructing a borescope system to look at the content of a cryogenic fluid tank on a space vehicle. Here is an example. Actually, people did something similar back in the Apollo era. This is a tank of Saturn V rocket, first stage, the kerosene tank. And then at that time, they actually used a fiber bundle to look at the window on top of the can because the temperature is too cold. You cannot place a camera sensor there. So the image was actually done through a fiber bundle. And then this fiber bundle, they need to be carefully crafted to make sure that the image is relayed out with high fidelity. And our lab was tasked with building something similar for a space vehicle. And at that time, we actually, due to their cost constraints, we actually get a bunch of optics and a relatively small fiber bundle pieced them together as an optical system. So we have an objective lens that look at the content, look at an object you are going to see, and then we have a fiber bundle that's sitting at the image plane of this objective lens. So whatever image being projected here will be mapped to the first port of this fiber bundle, and then the fiber bundle will transmit the image to the other facet. And the fiber bundle itself has a pattern like this one due to the non-uniformity of the fibers involved. And also, each of the fiber in this bundle is actually plugged in manually through a preform so that its precise alignment cannot be guaranteed. And then at the output facet, we put an in-house relay lens to project image back onto the camera. So now my camera sits far away from the object, and this is a borescope imaging system that we can now use to look at a challenging environment, right? So with the method I just described on the previous page, what we did is now we instead of looking at the object directly, we first replace the object with a computer screen. And then we light up individual pixels on the computer screen to mimic individual points in my object. And based on the theory, each point will form a speckle pattern or the point spread function on the camera. I record what is the pattern formed on the camera. So in this raster scan video, that's exactly what we are doing to calibrate this system. So now I have an exact system model that describes how each point in the object will become whatever shape on the image plane. Keep in mind here that each point at different locations of object may form a different shape of the point. The size of a point may be different, the shape of the profile may be different, and also the location may not be exactly may not be exactly following the order of the objects, since there are some skews in the fiber array involved in there. So basically, now I have a model of an imperfect optical system, right? And I can write it here. So with a bit of computational methods that I developed at that time, here is an example, and showing that how we recover an image. This is actually a circuit board, and well, we cannot show anything confidential, so we actually put a circuit board in there for this experiment. Because we need to publish a paper showing our method works. So, but we cannot show any confidential content, so we actually put a circuit board to demonstrate this method. This is the original object. And then I have my image formation model already calibrated. The N here will represent a bit of noise during the measurement. Now, this is the image we actually measured after it goes through the entire optical system. You can see that letters start to get blurry, and then you start to have the distortions, the straight lines becomes distorted here and here, and the letters are also distorted. This is because the fibers are misaligned in this fiber bundle. And so here's our measurement. But now I already know what's the system model here. So I can do a recovery of the original object by solving this optimization problem. So X is basically you minimize the discrepancy between Y, your measured image, and H is a system model we just calibrated, and X is a trial solution that you are going to you use. We keep refining this trial solution until the discrepancy becomes minimal. At that time, what we need to do with this one is that was during the time about 2016 and 2017 when I did my PhD, and if I was at the time when I did my PhD, this equation would be I would need to hand derive its gradient. So we know to solve a minimization problem, we derive its gradient. Now this is the gradient with respect to individual elements in this X, because remember X is a vector. We derive this gradient, and then every time we move along the gradient direction. Sometimes for complicated minimization problems, it's going to be quite tricky. And later, when it's 2022, AI becomes a hot topic. And there are lots of readily available software packages that can train an AI model. What is it doing essentially? It's solving an optimal problem, because in the AI model training, you are minimizing the loss function to try to tune your way to minimize the loss function. And exactly, we build a fake AI model. We say, hey, train this, right? Pretend you are training this, and then find what's the optimal X value that can minimize this. This is my loss function, so something like that. So I no longer need to hand derive the gradient with respect to each individual elements. I just build a fake AI model and let it train. So the PyTorch and TensorFlow actually were quite helpful in those regards. Yeah. Now, if we look at the reconstructed object, we can see that it resolved the distortion and all this blurry issue. And you can compare with the original object, you get the high fidelity. So this is this is something that we can calibrate an optical system, and then we can recover what the original measurement, what the original information of the object we are going to measure. If it works well, why do we need optics, right? Why do we need good optics especially? So the answer later I figured out is actually as a property with this matrix equation. We know that given a system of linear equations, sometimes you don't have a solution at all, right? Especially if you have conflicting equations. this becomes a case, let's say your measurement has noise, or if your calibration is simply not perfect. These equations may not have a solution. From a mathematical point of view, this is actually this is explained in terms of the singular value decomposition. So basically, given this matrix that we already built here, the matrix H, right? We build this matrix, and then we calculate its eigenvectors, all of its eigenvectors. Some of the eigenvectors have a 0 eigenvalue. Those locations form the null space of your linear system, and those are the things that you cannot solve. So most likely, yes, the solution, you don't have a solution at all, or the solution is not unique. Most likely, that's the case. So if I have a system with a points per function so big, the measurement will be blurry, and the equations don't have a well-defined solution. And now here's your solution. Horrible. If I have a system with a good points per function, the speckle pattern of each point of the object is so small, it's so confined, it's so well behaved, then this system matrix for my imaging system is almost an identity matrix, in which case the solution is just itself. So the reason we need good optics is not because we do not have the numerical method to solve for an imaging system. It's because the mathematical nature of such system with bad optics that they don't have a solution at all. That's why we need to build good optics. And that's why we need to minimize the points per function of this optical system. Now we know that having a small points per function is beneficial to an imaging system. We need to understand what causes it to enlarge. And first, we need to make sure we know how to measure the size of it, right? In astronomy, the easiest way to measure a points per function of your optical system is actually to look at a distant star. So if you look at the distant star, make sure it's not overexposed, right? If it's overexposed like this, you see the beautiful cross pattern of your telescope aperture, but that's not your true points per function. It's actually this one without overexposure. And then you count, hey, probably 5 pixels or 7 pixels. That's your points per function. Yeah, to measure it, you have to measure a distant star. So it has to be a distant star because it has to be smaller enough. Planets still have a finite size disk, and you cannot use that. So you measure a distant star without overexposure. That gives you the points per function of your astronomy system. Now, there are several factors contributing to the enlargement of the points per function. To surprise, optics is not the only factor. First, we have the motion and tracking error. Imagine if the system is sitting still and the Earth is rotating. Every point, every distant star will form like a star trail, right? So that enlarges your points per function. Every point, let's say a distant star is a point. Every point is mapped to a trail. And then we have the atmosphere turbulence. And then you can see here that the star will start to twinkle and wobble, and then creating these speckles that are larger than the true performance of the optics. To solve this issue, now we have adaptive optics, right? And of course, I don't have adaptive optics, so I'll leave it to the mercy of the weather, yeah, and also the higher level wind to make sure, yeah, I don't have adaptive optics, so I have little control on this aspect. Next comes the optics. After you solve these two issues, then it's the optics. Now, if we look at the optics, what are the factors contributing to the enlargement of the points per function? Now, there's a diffraction limit. Even if you have the perfect optics, you cannot focus a cone of light to an infinitesimally small point. This is due to the diffraction limit there. And then on top of that, if your optics contains aberration, then you will never reach your diffraction limited performance. So your speckle pattern will be even larger than that. So diffraction limit gives you a lower bound of the size of the point spread function. You cannot go below that. Normally, an optic system will have a slightly worse performance, right, because of the aberrations. So you will actually see the point spread function larger than the diffraction limit. So let's look at these two factors on the optics side, because that is something I feel more confident about. And then these adaptive optics, I don't have it. Motion and tracking error, hope for the best with the mount, right? So this is the diffraction limit, and we call it the Rayleigh criteria. So imagine you have a lens here. Oh, by the way, from now on, I think there are lots of Zmax plots that were actually part of the homeworks that I assigned to the student when I was teaching a class optical imaging, like optical system design. So all the solutions are already there. If you took my class, the solutions are already there. So this is a lens. And then let's imagine that we have two bundles of parallel rays coming from distant stars, and they are separated by a tiny fraction, the tiny angular separation delta here. They will be mapped to two different locations on the image plane here. Now, because of the diffraction limit, each of these points, even though your optics is perfect, each of these points will form a speckle. We call it array disk. And then likewise, this point also forms a speckle, also forms an array disk. The array disk has a finite radius that is related to its aperture and the wavelength. So you want to make sure that the minimum angular resolution you can resolve is actually the distance between these two is actually the size between the size of the array disk. In other words, if you have two array disks that are separated too close to each other, then you cannot resolve. There are 2 points in there. You just see one big point, and so that means this angular separation is not enough to be cannot be resolved by your optical system. Now, with this, another implication here is look at how large the array disk will be, right? So let's say this array disk, if it's 5 microns, 5 micron diameter across. Now, look at my camera sensor. If my camera sensor's pixel size is nowadays people can already make 1 or 2 micron pixels. In fact, the cell phone camera, they already have a pixel size that's around 1 micron, almost pushing the limit now. So if the array disk is already 5 micron in size and my pixel size is only 1 micron, yes, I do have 5 times more pixels than my effective resolution, but those extra pixels do not give me more information. So that's also another consideration here. So here, basically, we have 2 considerations. One is what's the limit resolution you can resolve, depends on your optics and aperture. 2, how large is this? How large is the array disk or the diffraction limited spot determines what is a most useful camera pixel size. So here, if you look at this plot for the aperture versus a focal length, every line here represents a certain f number of your optical system. And if you look at the Rayleigh criteria equation here, f divided by the entrance pupil diameter, that is your f number. So every optics has the same f number can be matched to a sensor with the same pixel size. So that's something that I realized that when I built my system, when I built my system, I actually took this into consideration. What camera should I choose to match with what kind of system? So that is the diffraction limit part. Diffraction limit governs the smallest feature, the smallest size of the point spread function. it governs the best case scenario, your angular resolution you can achieve, assuming you have perfect optics. Now, the second part is the optical aberration. So, this is a centuries-old problem. Starting from Galileo to Newton, we are all familiar with their version of the telescope they built. Galileo built a telescope with one convex lens and one concave lens. He built it from modifying the spectacle glasses, our eyeglasses at that time. And then Kepler improved the Galileo's design by swapping out this concave lens with a convex lens, because Kepler realized that a concave lens needs to be pretty large to cover a large field of view, and at that time, making a concave lens was more difficult. So Kepler changed it to a convex lens, and now that inverted the image, but it's not a problem for astronomy, since in the sky, there's no right direction of which side is up, which side is down. And then we are all familiar with Newton's version of the telescope. He prefers to use mirrors rather than lenses. So if you look at these designs, actually, these pioneers in the astronomy and in optics and astronomy, they also contributed to some of the aberration theory in optics. So let's look at their designs. So now we have their designs reproduced in Zemax. So in Galileo's time, he was using purely spherical lenses. And then in a spherical lens, what you see here is rays at different height of your aperture will be focused to different locations along your optical axis. This is called the spherical aberration. That gives you a spot, like a spot diagram, which is larger than your Airy disk. Here, this circle, the black circle, represents the size of the Airy disk, the diffraction limit spot size you can get. Kepler not only improved upon Galileo's design of the telescope, he was also the first to formulate this aberration mathematically, knowing that the rays bend according to the refraction law or the Snell's law, knowing that how the rays bend. He was the first to derive that in order to focus a bundle of parallel light to a perfect point here, you should not use spherical surfaces. You should use aspherical surfaces, and he was the first designer of aspherical lenses. Indeed, with his design, which turns the first surface here from a spherical shape into an elliptical shape, all the rays will focus to a point for this parallel ray bundle, and that's shining along the optical axis of the system. And now you have all the rays focusing to an ideal point. Your spot size is limited by the diffraction, so the Airy disk will limit your spot size. Now, after Kepler, Newton was the first guy to study the effect of colors. We all remember his famous experiment playing with a prism that separated white light into 7 different colored rays, as he called, right? That was actually due to the dispersion. The refract index of the different wavelengths or different color of the light is different even for the same material. Let's say for the glass, red light actually bends less compared to blue light. So Newton was the first to realize that even if Kepler made the perfect lens, it only works for one wavelength or only works for one color. If you have different color of rays coming in, like this picture shows you, and then the blue light will focus closer to the image plane, while the red light focuses further away into the image plane. And then there is only one wavelength that can, even if you have a perfect lens, there's only one wavelength or one color that can perfectly get focused onto your image plane. So that's what Newton realized. Then he said, hey, instead of building a telescope with lenses, we should use mirrors, because in reflection, the angle of reflected ray is always the same as the angle of the incident ray, regardless of color, regardless of wavelengths. So that's why Newton proposed to build telescope with mirrors. So that's actually a centuries-old effort to reduce optical aberration here. And notice here that this analysis, we are only looking at some ideal scenarios because we are only looking at the rays that goes along the optical axis. For the rays that are tilted, that are at an angle to the optical axis, and then you will start to introduce even more aberrations, which are not described here. But this actually gives an idea of how the theory of aberration was developed. Kepler, what he realized was called the monochromatic aberration, and Newton, what he realized was the chromatic aberration. So, okay, so that's basically an overview of what I learned during my PhD dissertation, right? So does that mean I'm ready to build the telescopes? Absolutely not. In fact, the first one was a failure. The first prototype I built, at that time, I have not even passed my candidacy exam, and I built one. Why I was so in such a hurry to build one? Because there was a great American eclipse in 2017. So, and I need a system to try to image it. And rather than taking a picture and post it on Instagram or Facebook, I want to get an image that I can, that I feel it's more scientific, right? So I rushed to build a system. I got a stock camera lens. That was actually a zoom lens. A zoom lens does not have a perfect corrected optical system because it needs to make sure that you focus relatively well for different focal lengths. So it's actually not even a perfect optical system. And then I put a camera adapter onto a C-mount camera, and I inserted some ND filters inside the tube to reduce the intensity of light from the sun. During the eclipse day, all I got was one picture showing 3 sunspots along the intensity profile. And I did not get a picture of the total eclipse with this setup. This was actually taken with, I realized I cannot take the picture with this setup, so I just bring out a camera and take this picture. So the problem with this one is an obvious violation. Remember those 3 factors contributing to the size of the point spread function? The problem with this one is an obvious violation of the first one, the motion error or the tracking error. There's no tracking, sun's moving, and I only get one picture. That's it. It's a failure. So I thought I was ready, right? But I thought with a PhD in optics, I was ready to build my system, but not. So when I passed my defense in 2020, I built my prototype 2, and this time it kind of take into considerations even more factors that I think will make an optical system that are suitable for astronomy. First, I add a tracking mount. This is an equatorial mount with tracking at a sidereal rate along only the RA axis. And then, same camera, and then I have a different lens. This is a Markov reflector. It is a mirror-based design, and then it has a glass plate in its front entrance that serves both as a corrector plate as well as a secondary mirror to bend the light backwards and form the image on the camera on the image plane. So that was the optics I used, and here I have, at that time I started to learn that I need to do polar alignment, right? And then I put everything together, set up like this, put my computer there to control the whole system, and sure enough, got some results. And here are some of the results and the lessons I learned just from this prototype. The first was in 2020, we had a comet Neowise that visited us. It's a long period comet that only comes like once in our lifetime, right? Because the period is thousands of years that we may not see another one in our foreseeable lifetime. So it's a long period comet. So when the Neowise came, I brought out this setup, and then now it has some decent amount of tracking again, but there's no guiding. So it cannot track, it cannot always follow the star. But for comet, it's actually quite okay, since for the comet, if you guide with the background star, the comet itself is moving, so you cannot take super long exposures anyway. So we got the image of the comet Neowise. What other things I did with that? So that was actually a surprising experiment I took with that system. So on July 19th, 2020, that was shortly after the Neowise came at the end of that year. But before that, in July, there was a great conjunction of Venus and the Moon. The separation was so small that they actually fit within the field view of the telescope lens. And when I got the image, I was puzzled. We know that the Moon, although it's a new moon, it's still orders of magnitude brighter than Venus. But actually on the image, if you read the pixel count, the pixel value, you realize that the Moon is so much dimmer than Venus. And in fact, this image here I'm putting there was actually adjusted with PowerPoint. And these are the original values. If you plot in the original linear scale, you can hardly see the Moon at all. In the PowerPoint, I adjusted the contrast so that at least we can see the Moon here. But these are the pixel values of the Moon and the Venus. Moon is order of magnitude greater than Venus. In fact, if you calculate it, it should be 75.8, one order of magnitude, almost 2 orders of magnitude more brighter than Venus. But the pixel value is actually 1/10, less than 10% of Venus. Why? Now at that time I realized that what we call the apparent magnitude, it's a large scale quantity, or in photometry, in optics, we call it a luminosity. This is measured in the energy emitted per unit time. So what we call the magnitude of an object, of a star or something, we are measuring the total amount of energy it emits per unit time. What we actually capture on each individual camera pixel is proportional to the radiant intensity, which is measured in energy emitted per unit time per receiver angle. In other words, radiant intensity is really the metric that's proportional to your pixel readout. It's not your apparent magnitude. It's not your total magnitude of the object. It's the radiant intensity that really matters. So if we do this calculation, we know that the Moon is 75 times more brighter, overall more brighter than Venus. But if we factor in their size, Moon is half a degree or 1800 arcseconds, and then the area should be squared. Venus at that day was 50 arcseconds, almost 1 arc minute, which is the human's visual, which is almost the visual the resolution limit of human eye. If we factor in their size, and then we divide the overall intensity divided by the size, then we get the radiant intensity ratio, which is less than 10%. So it is expected that each pixel on the Moon is less than 10% of each pixel of Venus. Okay, so mystery solved. Another thing was actually also towards the end of 2020 that we have some of the reports actually call it the Christmas star because it was also another conjunction, and the closest conjunction of Jupiter and Saturn. And for that one, I did the observation following these consecutive days, while one day was missing because it was cloudy. And then I map out the location of Saturn relative to Jupiter on those days. And then I plot this line, find this find this perpendicular, draw this perpendicular line here, and then in Excel, I was able to calculate exactly when they reaches the closest conjunction. So if you calculate with this one, and then you plot it, you realize that the closest conjunction happened during the daytime, which was actually true because later I look up in the sky.org and then look at this grand conjunction Jupiter and Saturn. Closest conjunction happened in the daytime. Yes, so not at the nighttime. So by the time we look at the night of December 23rd, Saturn has already passed the closest conjunction. And another thing we also trying to do it was, so this is Jupiter, right? And if we zoom in, we can see 4 of its Galilean moons, and then they are aligned along the ecliptical plane of Jupiter's orbit. And then Saturn travels along this course. So we were able to see that, hey, there is an orbital inclination between Jupiter's orbit and Saturn's orbit. Since Jupiter's orbit we can represent with the ecliptic plane of its 4 moons, and Saturn, we know its trajectory. So there's about a 1 degree difference, which also shows up here. So that's my prototype 2, and that's all the experiment, like that's all the successful experiments I did with that. Moving forward, and after I graduate, I stayed in UCF as a research scientist, and at that time, I was also teaching the class Optical System Design. So this was actually some contribution also from the student who took that class, because this was once a homework problem. I thought I need to have a system, right, for astronomy that I actually am fully aware of its performance, how it is going to behave, how does optics going to behave, how well the optics can be, right? And I decided that I need to have a reference design for all the models. Let's say if I'm going to buy this lens, if I'm going to buy this piece of optics, I need to have a reference design for it so that I'm confident that what I'm buying will behave according to what they advertise, okay? And since at that time I was teaching a class, Optical System Design, I thought this may be a perfect homework question problem for the students, right? Yes, indeed. So I was thinking about buying this lens, Oscar FRA 400. So it's a 400 millimeter focal lens, and the aperture is 72 millimeter, so almost f5.6. And I know that they advertise it, that this is a quintuplet design, so 5 lens elements. And with a bit of thinking, 5 elements, 3 of them goes to the front apochromatic triplet. This is actually, in order to cancel out the chromatic aberration, you do need to use cemented glasses with different materials so that they have so their dispersion properties is reversed against each other, and you can cancel the effect of the chromatic dispersion for several of the wavelengths. And then I will add 2 more as a flattener. And then I ask my students, at that time we just finished the lecture on designing an achromatic lens system. And then a few weeks ago, we talked about field flattener. Then I basically assigned the homework, say, hey, design an optical system with 400 millimeter focal length, f5.6, using 5 elements, and then pick the materials that you can get from Adamant Optics. Those Adamant Optics has a list of preferred glasses because those are easy to use. Those are commonly used glasses. Pick materials from that. Pick 3 different materials from that. Use 3 different materials for the first achromatic triplet, and then use probably the same or different materials, either 1 or 2 materials for the field flattener. So I ask the students, can you design such a lens? And I want to see the performance. Among all the designs, this is the best one I received, and then I looked at performance. Okay, it's relatively close to the diffraction limit, so I think it can be a good optic system. So without hesitation, since one of the students got this, I think, and I validated myself, good. Without hesitation, I bought it. So actually, my students actually helped me a lot with this homework. And I know there are 25 students in the class, and yeah, if everyone came up with a design that is definitely going to be the best design, and I just look at the best design, the performance, and validate it myself, so that I know such design is feasible and it can meet the good performance. So thanks to the students who took the class and who actually helped with this homework. So that's the optics. And then I actually switched to a heavier duty mount, since this thing itself, because it's made of 5 pieces of glasses, is pretty heavy. So I need to have a relatively heavy duty mount. So I chose so Skywatcher SG-EQ5. And then I built up the peripherals, like your focuser, electronic focuser, and then a mini computer to control everything. I built out the peripherals. At that time, I also started to use Nina. So since I have a mini PC, I run Nina on it to control everything. And later, this actually proved to be a valuable experience for me. Later, when UCF Observatory asked me to look at their equipment. So we start to build a recipe in Nina, an imaging recipe in Nina. So first, hey, move to this target, take several pictures, and then for certain durations, take certain number of pictures with certain durations, and then after you finish everything, move the telescope to the home position, and then turn off the computer. So I can let it run unattended for the night, right? So I don't need to stay there. And I know Nina is guaranteed going to turn off the computer before the battery runs out. Since otherwise, if the battery runs out, computer shuts down itself, there may be some data unsaved. So that was the time I also learned to use Nina. And then I also during the same time, since I'm now taking lots of images, I need to stack them. So I start to use a serial for the image stacking. And we've also figured out a recipe here that if we are going to stack the SHO, like sulfur 2, hydrogen alpha, and oxygen 3, the different narrowband channels, what we are going to do is we first do the registration, but after we do the registration, before the stacking, we are going to remove the stars. So, and then do the stacking of only the nebulars or the galaxy features, and then recompose the stars back onto it. So that at that time, I also kind of played with this recipe. Now, this, I call it Astronomical Imaging and Metrology System. This name I gave it after I came here last year, after I joined the industry. Before, it was just maybe another name, the Prototype 3. But after I joined the industry, I realized I need to give it a name so that so that it reflects its purpose and yeah. So, and the AIMS seems to be a good name for it, and the Astronomical Imaging and the Metrology System, so comes the name. Otherwise, this will be called another Prototype 3. Now, let's revisit this page. So we have Prototype 1, which was a failure. Prototype 2, Generation 1, along this line, along the line of f5.6. And I have a camera which is using the Sony IMX571 sensor with a pixel size matching its diffraction limit. Now, at that time, I realized these systems, they can take pictures of the targets that are relatively large in the sky. In other words, it has a large field of view. What if I want to image planets or the planetary nebulars? They have relatively small size. I need something with a much longer focal length to zoom in to the target. And for that, if we use something with very long focal length, it's very hard to maintain f5.6 anymore, because it means you will have an enormously large aperture. So instead, I settled on f8 and then find my generation 2 gear in this way. So generation 2 actually fill in this region on this chart. Generation 1 all fell along the line of f5.6. Generation 2 fell here. And then at that time, I also got a camera that's using IMX294 sensor with a relatively larger pixel size. And I thought, hey, this pixel size will match the angular resolution of my generation 2, because the diffraction limit of that, even assuming your optics is perfect, the diffraction limit will already give you a size that's relatively that are larger than this one. So here comes the generation 2, and this is generation 1 and generation 2 working together on the Lake Observatory during the evening with the stars night back in August last year, and I actually showed this picture 2 months ago. Generation 2, I started with I must have a focal length that's way longer than generation 1, so I settled on 2 meters. And then 2 meters, and then I realized that a Ritchie-Chrétien design, which was actually also a homework problem, so thanks to my students again, it's also a homework problem. A Ritchie-Chrétien design actually gives you a relatively fast focus, a larger aperture, given if you have the same focal length. I look at several Celestron Schmidt-Cassegrainian designs. For longer focal lengths, usually their f number or their aperture will be relatively small, so there will be a much slower focus. And I thought for imaging, it's better to have relatively fast focus so that I don't need to integrate for such a long time. So generation 2 starts again with these spec sheets. And what I do is ask my students, when I get into the lecture portion about the reflective telescope, ask my students, hey, now I'm going to build a 2-meter focal length telescope with mirrors, and then I want an aperture of f8. Can you make a reference design for me? Sure enough, they made me a reference design, and that's it. From all the homework submissions, I got a reference design, and I realized that this reference design, from the overall size and the tube length, they actually match what they advertised on the web page. So I think, hey, that's probably it. I got my reference design now. Now, the problem with this is a Ritchie-Chrétien design, and we know that any reflector telescopes, they need to be collimated well so that your image is free of all the artifacts or free of all the aberrations. But with this thing, the collimation is not as straightforward as a Newtonian telescope. So here, in a conventional Newtonian telescope, you have a mirror center mark here, and then you put in your laser collimator. From here, bounces off a secondary mirror. You adjust your secondary mirror until that laser light hits the center of the primary mirror, and then you adjust the tilt of your primary mirror so that the reflected light reflects back into a laser collimator. It's relatively straightforward, but for the Ritchie-Chrétien design, the secondary mirror and the primary mirror, they are both aligned along the optical axis. So if I shine the laser light here, first of all, it will hit the secondary mirror center mark, but it can only tell you whether the secondary mirror is the correct tip and tilt. And most of the time, it doesn't even work because there will be some baffle, the baffle to block the straight light on top of the secondary mirror. So it's actually hard to see where the laser hits on the secondary mirror. So, okay, so how did I collimate this one? And this time, well, it was not a homework problem for the students. And I did decide to do it, give it a bit of thought myself. So in optics, when we always do an optical design, there is something called a sensitivity study. So we want to know that if I have a lens group, and let's say there are 3 lenses or 5 lenses, what are the effects to your image quality if the lenses are perturbed away from their nominal positions? And this is called a sensitivity study. So I did something similar. Why not I run a sensitivity study on the best submission from the students and see how it behaves? And sure enough, this is the picture. This represents that the two most critical parameters, the tip tilt of the primary mirror and tip tilt of the secondary mirror, on the x and y axis respectively. The z-axis is the size of your spot. In other words, what is the size of your point square function you are going to see? With this sensitivity analysis, we realized that for the same amount of change in the mirror tip tilt angle, secondary mirror gives you a much larger spot size. So secondary mirror is more sensitive in this system, and then primary mirror is less sensitive the image quality is less sensitive to the primary mirror offset. Another thing we realized is if you look at the spot size under no misalignment, perfectly focused, and now if you change the distance between the primary mirror and secondary mirror, this is not working at its design, the focal length. Since in this design, both mirrors will have optical power, they will bend the light, they will focus the light, they will focus or diffract, or they will focus or deviate the light. So both mirrors contain the optical power, and also both of the mirrors are hyperbolic shape. So if they are not working under the intended focal length, your point square function is actually also larger, even if assuming you don't have any misalignment in the tip tilt angle of these two mirrors. So that's another thing to pay attention to. So here's a two-step process that I eventually use. First, get the telescope in focus, adjust the distance between secondary mirror and primary mirror, pay no attention to whether the tip tilt is correct or not. Once we made the adjustment, we use a place solving and look at one of these important factor here called pixel scale. This tells you what is the angular size each pixel represents, and we can easily calculate it based on the Rayleigh criteria example I showed you earlier. So let's go here. Yes, we can easily calculate this. Now imagine here I set this separation between the two array disks as my pixel size, and then this is the focal length. So the pixel scale is just the arctangent of your pixel size divided by your focal length. So comparing to what the place solver gives me on the pixel scale, I can actually determine, and I know the camera's pixel size, I can determine whether my focal length is correct or not. So I first adjust the distance so that the focal length is correct. Then we start to adjust the primary mirror and the secondary mirror to make sure they are centered. Here is an image that you can remove the camera and look directly through it. You will see that the image of the secondary mirror and then the image of the primary mirror. To make sure there's no tip and tilt, we basically visually make it concentric, make all these rings concentric. And this might be an iterative process, since every time you adjust the primary mirror or you adjust the secondary mirror, everything will change a bit, right? So you will need to do an iterative process until they visually look concentric. Now, is that good enough? So we test on the distant star to see if it's good enough or not. Turns out that it's pretty good, and the visual alignment turns out to be pretty good. So here's the point square functions as I perform a through focus scan. So we have we move the focuser out versus move focuser in. We start to see this concentric ring, and we start to see the rings. And the rings, they form a symmetric pattern across your entire field. This actually agrees with the simulation from Zemax. Another thing is if we look at the center, and we focus this star in the center, and then we put on a focusing mask. Now, if we rotate the focusing mask by 90 degrees, we know that it's also focused. That means I eliminate the comma or astigmatism of the center spot. So your entire field, the spot across the entire field is symmetric. And then the field at the center of the image is also free of comma and astigmatism. And now I realize it is collimated well. So that's actually how I collimated this. Again, thanks to the model created by the students, I now have a reference design and I can do the tolerance analysis on top of that. And we also noticed something interesting here. if you look closely at the defocused spot here, in the center, it's a dark in the center, but in the center, if you zoom in, you actually see the Arago spot in there, or the Poisson spot. This actually is an interesting story that people debated whether light travels as rays or waves. So there were two factions at that time. Newton and Poisson, they believed light travels as particles that follows a ray-like trajectory. And Huygens and Fresnel, they proposed that light should travel as waves. And then there was a scientific committee asking people for proposals on explaining the behavior of light. So Poisson was serving as a committee, and he read Fresnel's paper saying that light travels as waves, and he did some derivation himself. So wait a moment. If light travels as waves, then if you have a circular disk, you will actually see a bright spot behind the circular disk, since the waves will interfere constructively at the center of that disk. He thought it was ridiculous, because how can you see a bright spot behind a circular disk which obstructs the light? And this is also the case for the secondary mirror. In fact, there's no direct rays passing behind the secondary mirror along the optical axis. You can see that because of this obstruction, the rays bouncing back of the secondary mirror only gets to the focus. You only see the light at the center of this, along the optical axis of the secondary mirror at the focal point. If you defocus it, you are not supposed to see any rays on this area. Yet, you do see a bright spot here. So Arago performed the experiment and first noticed this bright spot behind a circular disk, and hence it's named the Arago spot or Poisson spot, proving that light will travel as a wave if we are talking about the scale, if light is interacting with an object whose scale is comparable to its wavelengths. So here is actually, so this is the geometrical representation of that. We'll see that there will be no rays traveling along the optical axis of the secondary mirror. But if we use wave optics to calculate the electrical field, then we realize that after certain distance, pretty close to the secondary mirror, you start to have a bright spot. And that is what we observe here. So this is actually a perfect validation that light travels as waves. It's more accurate to describe light as waves. Of course, the rays works well for a much larger size scale. And here are some of the images of generation 1 and generation 2 that I also showed 2 months ago. And generation 2, so now we can start to focus on the planetary nebulas, and which are too small of a target for generation 1. So all of this learning eventually paid off when I worked on the UCF's Robinson Observatory. So the Robinson Observatory was actually a observatory at the University of Central Florida for the teaching and education purpose, teaching and research purposes. It's managed by the department. It's managed by the College of Science and then the Planetary Science Group, and then it received a major renovation back in 2023 to further its research and outreach activities. Before, the observatory was known for its occultation measurement. So if you have an asteroid body blocking a distant star, you can use the duration of the occultation to measure the size of this body. And this is a relatively fast process. And after renovation, they start to bring out the Nights Under the Star events, in which they are going to showcase those nebulas or galaxies, those deep sky objects to the students. So before they only did the occultation, so that was a relatively fast event, right? So if you have the entire motion system that will accumulate some error in a long time, it doesn't really matter. But if you really start to imaging the deep sky objects, it becomes a problem. So using what I played with Nina for my generation 1, generation 2 setups, now I apply the same thing to the observatory. And first thing first, I installed a guide camera along its finder scope. Since this observatory is fully computer controlled, so the finder scope becomes redundant, but it becomes a good place to install a guide camera so that you can guide it even if your tracking rate is perfect, right? And then we have everything under control in Nina. So we work with the vendors to get the drivers for each of these, including the domes, the switches, and this is a plane wave mount. And then the rotator, focuser, and the mount itself, they are all connected through a plane wave interface, so that you don't select individual rotator or focusers in Nina. Instead, you connect to this interface. When you select the device, you first need to connect to this interface, and then through this interface, you access the rotator and focuser on this plane wave interface. So with a bit of hassle, we got everything to work in Nina, and now I can put in my recipe. Remember earlier I said we can write a recipe, a sequence in Nina that tells it how many images to take for what duration. And now with this everything under control in Nina, including the dome, we can write an imaging recipe and let it run automatically. So one of the interesting facts here is this. Here it's connected to a 4-port switch at the focal plane, and then remember earlier we mentioned that this observatory was used for both education and research purposes. So we actually switch different cameras. So we have a monochromatic camera for imaging with filter wheel for imaging, and then we have a color camera for outreach. For those things, the students don't want to wait for the time to stack the image together and then you combine all the color channels. They don't want to wait for that, so we directly use a color camera for that. And then we retain the original camera, the QHY CCD, that has a precise timing for occultation measurement. And then we add one port here that leaves one port open for the research activities, the astro-photonics, a research direction called astro-photonics. For those research groups that uses this port 1 for astro-photonics, they actually installed a fiber spectrometer unit, attach this to this port so that you can look at the spectrogram of individual stars. And recently there is a research effort at the university to use frequency comb laser source to beat with certain spectral lines from the distant star, so that you can measure precisely what is the red shift or the blue shift of the spectrum. And that is an ongoing research activity at the observatory. And then so we install this 4-port switch, and then we can make sure the observatory can now be used for both imaging, outreach, and for astrophotonics related activities. And here are the images taken from the observatory after we fix everything. So we install the guiding system so that the tracking is now stable enough that allows us to do unattended imaging throughout the entire night. Of course, the policy does not allow remote observing, so I still slept several nights on site to keep an eye on the observatory. But when I sleep or take a nap, I let my Nina recipe run in the background, and for 2 nights, we got the Eagle Nebula in the Hubble palette. And then we also got the Ring Nebula and Dumbbell Nebula, and these are other planetary nebula targets from the observatory. So proving that this thing is now working. So with this thing working with the correct motion and the guiding system, before it can only do occultation, which is a relatively fast event. Now we expand its capability to do both occultation, imaging, outreach, and astrophotonics research activities. For astrophotonics, if they are capturing the spectrogram of a distant star, you also need the guiding and the tracking to be accurate, because you need to stay at the star for a long time. The signal from the distant stars are very faint. So now we kind of restore the eyesight of the observatory to its best working condition. So that wraps up for my talk, and that's all I want to share with you about my learning and either success or failures and achievements and everything. So thank you for your time, and I'm happy to take any questions if you have any.
Any questions for our speaker?
When you're going from your Ames 1 to Ames 2 system, you went from a system that was unobstructed and then an obstructed Ritchie gradient, I believe.
Yeah.
Did you factor in I guess you call it the spot size due to the diffraction caused by the secondary?
Okay, so the question is, yes, did I factor in the spot size caused by the obstruction of the secondary mirror?
Right.
Yes, correct. Yes. So for the Zemax simulation here, we factor in the obstruction of the secondary mirror that creates the obstructed aperture area on your primary mirror. And of course, when the light bounces off the primary mirror, it's already obstructed. But once it hits the secondary mirror, it will have no further obstruction. So yes, for the incident light, we remove the aperture area obstructed by the secondary mirror. But once it bounces off the primary and reaches the secondary mirror, then there will be no obstruction on the secondary mirror. And we also added the two vertical spikes of the secondary mirror on top of that, so that you can see that in the simulated spot size, let's say this is the defocused spot size, you can actually see the spike pattern, that cross of the secondary mirror, the cross mount of the secondary mirror, as well as the secondary mirror obstruction itself. Now, if we look at the electric field distribution, you can see that these are weakened area caused by the crossing, and then this is the secondary mirror obstruction. Yes, so when I calculate the spot size on this plot on the sensitivity analysis, it includes the obstruction from the secondary mirror. Yeah, and it's modeled it's modeled at this entrance plane here.
Any other questions?
I had a question about the pixel size, the optimal pixel size for your imaging system.
Right.
I think I've heard this referred to as oversampling or undersampling.
Correct, yes.
And what's undersampling? I can imagine you can resolve, your diffraction limit is smaller than your pixel size, so you're losing some sort of resolution. What's the downside of oversampling?
So oversampling, you mean your pixel size is larger than the diffraction limit or smaller?
Smaller.
Smaller.
Yes.
Yes. So in that case, I prefer to have slightly larger pixel size, because if the pixel size is too small, then that pixel will become more noisy. Yeah. Yes. So the signal to noise ratio of a camera pixel is actually proportional to the pixel size. So for those high-end DSLR cameras, they do like to use 5 micron or even larger pixel size, because if the pixel size is larger, it's basically a larger area photodiode that will give you less readout noise, thermal noise, and make your signal-to-noise ratio better. So if my resolution or diffraction limited resolution is already, let's say, 5 microns, I don't want to use 5 1-micron pixel to collect it. I'd rather use let's say, probably a 4-micron pixel size or something to collect it. Yeah, because your signal-to-noise ratio also matters. Yeah.
If there's no other questions, let's thank our speaker one more time. Excellent talk, Dr. Xu.
Thank you.
So thanks everyone for coming out this evening. Next month, I think we have another speaker. I forgot what the topic is, but hopefully see everyone in January. And Happy New Year.